Welcome back, everybody. In today's tutorial, you are going to learn how to code the policy gradient algorithm in Tensorflow 2. You don't need any prior exposure to reinforcement learning. You just have to follow along. Let's get started. Before we begin, a word from our sponsor. This video is of course sponsored by my Udemy courses, where I show you how to turn deep reinforcement learning research papers into PyTorch code. We cover actor critic methods and deep Q learning. The sale is going on now and the links are in the description. Let's go ahead and get started with our networks. We only need a couple imports for this. We will need Keras. This will be for the derivation of the class. We will also need our layers, which in this case will be a simple dense neural network. We're not going to deal with convolutions because the lunar lander environment is one-dimensional, so we don't need a convolution to handle any screen images. So our policy gradient network will encapsulate the functionality of our deep neural network, and that derives from keras.model. Our initializer is pretty straightforward. We'll need a number of actions and a number of dimensions for the first fully connected layer as well as the second fully connected layer. We will call our superconstructor, and then we go ahead and save our member variables. And here n actions is an integer because we're dealing with an environment with a discrete action space. That is what policy gradient methods are most well suited for. Then we have our first fully connected layer, and that outputs self.fc1 dims with a ReLU activation. Now, one really cool thing about Tensorflow 2 is that the input dimensions are inferred. We don't have to specify them. That is kind of handy. It's useful, especially if you don't know the exact size of the inputs. If, let's say, you're dealing with a batch of convolutions, if you're dealing with an environment in which you're interested in the screen images, like, say, Atari games, that's very useful. Our second fully connected layer outputs FC2 dims with a ReLU activation, and pi we will call our output layer, and that outputs self.n actions with a softmax activation. So the policy gradient algorithm basically seeks to approximate the agent's policy. The policy is the mathematical function that determines how the agent will act. It is a probability distribution, so it assigns some probability to each action in the agent's action space given some state or set of states. And so it's a mathematical function. We're going to take its gradient later in the learn function for our agent, hence the name policy gradients. And our call function, this allows us to actually perform the feed forward of our deep neural network. Takes the state of the environment as input, and you just pass that state through the first fully connected layer, and then pass that output through the second fully connected layer, and then pass that through the final layer, pi, and of course return pi. We don't have to worry about the activations like, say, with torch. You have to say torch.ReLU, for instance, because the activation is handled right here when we specify our layer. So that is it for our network file. Now let's move on to the agent's functionality. So here we will have a significant number of imports. We will need TensorFlow. We will need the TensorFlow probability package. You may have to do a pip install on that. I'll double check before we run the code. You will need the optimizer from TensorFlow optimizers import atom. We'll need NumPy, and from networks we will need our policy gradient network. Now we are not we're not using a memory class. We're just going to keep track of the previous episode using a list, and then convert the states and such to TensorFlow tensors. So we don't have a separate memory class because we're not keeping track of anything more than one single episode of memory. So there's no real point in making an entire class for the agent's memory. So our agent class takes a number of parameters as input. Alpha will be our learning rate. Give it a default of 0.03, a gamma of 0.99. We'll just use the default n actions of 4. We will default FC1 dims to 256. And then go ahead and save our parameters. As I said, our memory will be handled by a series of lists. We will need to keep track of the states, actions, and rewards the agent received. We will need a policy, and that is just a policy gradient network. And we will need to compile our policy with our atom optimizer and learning rate defined by alpha. Next, we'll need a function to handle choosing an action, and that takes an observation of the current state of the environment as input. The first thing we want to do is convert that NumPy array to a TensorFlow tensor. So TF convert to tensor. And we have to wrap the observation in a list to add a batch dimension. All of the dense layers from Keras expect the input to be two-dimensional, so we have to add an extra dimension to it. And I'm going to specify a D type of TF float 32 just to make sure our data types are nice and self-consistent. And then we want to go ahead and pass that state through the policy network. And that gives us the probability distribution for choosing each action. Recall that there's a softmax activation. If you're not familiar with the softmax, it's just an exponential of something divided by the sum of the exponentials of the set of somethings. So it'll give you the relative probability of selecting each action in this case. And we can use that to define a categorical distribution called the action probs or action probabilities. TFP distributions categorical. The categorical distribution is what you use when you have a set of discrete classes and you want to choose one of those classes with some probability defined by probs, in this case the output of our deep neural network. And then we want to sample that. And then we return the NumPy array's 0th element. We have to convert action to a NumPy array because it is a TensorFlow tensor, which will not fly with the OpenAI gym. And we take the 0th element because we have a two-dimensional output because we had a two-dimensional input. Then we need a function to store a transition in the agent's memory of the current episode. And this is just in a simple append operation. And that is it for our simple memory function. Now we need our function to perform the agent's learning. So the first thing I want to do is convert the actions and rewards to a NumPy, to a TensorFlow tensor, much like we did up here. Then we have the rewards. And then the next thing we want to do is calculate the discounted sum of future rewards that follow each time step. So what that means is we have a memory of the actions the agent took and the states it encountered and the rewards it received. So at each time step, there is some number of time steps until the end of the episode, and the agent receives some sequence of rewards following the current time step, right? In reinforcement learning, we typically discount future rewards for a number of reasons. It can be done to ensure that the sum over future rewards stays finite when you have a continuing task, because if you sum up rewards for a task that never ends, you get an infinite number, right? And that's not typically good for deep neural networks. It also helps to account for the fact that the agent has some uncertainty in the probability it will receive those rewards again in the future. So it received those rewards as a consequence of the trajectory it took through the episode, and that was defined by some probability function. That means it could take different actions given the same states in the future because it's probabilistic, and so it doesn't know if the sequence of rewards is guaranteed. So it discounts them to some degree by the factor gamma, which is less than 1, which ensures that we get a decreasing contribution over time. And so we have to calculate the discounted sum of future rewards that follow each step, the current step, that follow each present step in the episode. So we're going to iterate over the agent's memory and calculate a discounted sum. And so we'll have an array and called g, t in range, len rewards. So we're going to iterate over the agent's memory. And for each step, we set the sum of the future rewards to 0 and a discount factor to 1 because it's the present step, gamma to the 0th power. So for k in range, t len of rewards. So this will go from the current time step all the way to the end of the episode. So the sum is going to be the rewards at that time step multiplied by our discount factor. And then we have to multiply our discount factor by gamma. So we're increasing the discount factor by a power of gamma at each time step. And then the sum of the rewards that follow the tth time step is just given by g underscore sum. Now I go over this in more detail in the course. This is just a Python implementation of a mathematical formula. If you see the formula, it makes a little bit more sense. But this is kind of what it looks like in code. And again, I explain it more in the course. But the long and short of it is, it's just the discounted future reward that follows each time step. Next, we have to handle the calculation of our gradients. So TensorFlow has this neat construct called the gradient tape that allows us to calculate the gradient, in this case, at each time step of the episode. And this is new to TensorFlow 2. In previous videos, I'd attempted to do the lunar lander environment using deep Q-learning in basically the same way you would do it in TensorFlow 1.something, and it was very slow, very clunky, didn't work very well, and it's because I did not use the gradient tape. That is the way to do it in TensorFlow 2. It is operator error, of course. So what we have to do is go back through the memory. So we'll say IDX G, the reward, and the state, and enumerate. So we're going to get the integer integer index, the discounted sum of future rewards G, and the state in the agent's memory. We're going to enumerate the zip of G and the state memory. So then we're going to say that we want to convert the state to a tensor. Again, we have to add a batch dimension. And then we're going to feed it through our network. Calculate our action and probabilities. And then calculate our log prob. So the gradient function is proportional to the log of the probability, the log of pi. The derivation to that is given by the textbook Sutton and Bardo. It's free. You can look that up online. I covered it in the course, but if you want a free resource, check out the Sutton and Bardo textbook. Sutton and Barto are the authors. They're kind of the OGs of reinforcement learning, and they talk about the policy gradient theorem, where all of this is derived. But you want the log of the probability, and that is related to the gradient. The gradient calculation involves a log over the probability. And that's given my action probs.log prob of the action the agent actually took at that time step. Now, You may wonder, why are we doing this computation twice, right? We're doing the calculation of the distribution here as well as up here in the choose action function. Why not save the log prob up here? And you can do that in PyTorch, but in TensorFlow 2 it doesn't work, because then the log prob doesn't get added to the graph. You see, only the operations in the gradient tape context manager get added to the graph for calculation. My nomenclature may be a little bit loose here. What I mean is that only the things within this scope are used for the calculation of the gradients. These calculations up here in the choose action do not go into the calculation of the gradients, and so saving that value there is just the same as saving any other scalar value. Its gradient will be 0. Down here, it actually takes the derivative with respect to the parameters of the deep neural network, and so we have to calculate it again, basically. So then our loss is given by minus g times the log probability, but remember we have that batch dimension, so we have to squeeze it to get it down to a scalar quantity. And so this may seem mysterious, so why do we have the minus there in our loss? This is what is called a gradient ascent algorithm. So by default, deep neural networks optimizers will use gradient descent, but we don't want to minimize this. Here, what we want to do is maximize its total score. And so this parameter g is the discounted sum of future rewards. And so we want to maximize that, right? And you want to maximize the actions that have the highest probability of giving the highest possible rewards. That's the gist of the policy gradient algorithm, is that it maximizes the probability of selecting profitable actions while still assuring some non-zero probability of selecting other actions, which is how it deals with the explore-exploit dilemma, because it's a probability distribution, a probabilistic function. As long as the probability of all actions is non-zero for all states, you have dealt with the explore-exploit dilemma, which, if you're not familiar with it, the explore-exploit dilemma refers to the dilemma every agent faces. The agent is tasked with maximizing its total score over time, but it does not have a complete model of the environment. If you had a complete model of the environment, you could just plug that in and solve a set of equations. You wouldn't need reinforcement learning. So the agent has some uncertainty around what it thinks the future rewards will be, and it's never certain that it knows the best possible strategy. So it has to spend some amount of time taking exploratory actions versus taking greedy actions, those that it thinks are best, and the extent to which it engages in either of those two activities is called the explore-exploit dilemma. So outside of the context manager, we can go ahead and wrap up our gradients. So we say gradient equals tape.gradient loss with respect to what? Policy trainable variables. If you don't know where that trainable variables comes from, it comes from the derivation from keras.model. And then we can apply those gradients. So we say self policy optimizer, apply gradients, and this expects a zip as input. Zip up the gradient and the trainable variables. And then at the end of every episode, we're going to go ahead and zero out our memories. Okay, that wraps up our agent class. Now we're ready to code up the main loop and see how it performs. Okay, so we begin with our imports. So we will need gym, numpy, we will need our agent, and we will need a simple plot learning function. You can do a git clone of my GitHub repo. It's just a matplotlib pyplot with labeled axes. It's nothing mysterious. You can just do a pyplot of the scores versus time if you wish. You don't really need this. This is just a utility function I've written. It's available on the GitHub, but it doesn't do anything magical. It's just a plot. So our main loop, we'll start by instantiating our agent with a learning rate of 5 by 10 to the minus 4, a gamma 0.99, 4 actions for our lunar lander environment, and I'll use the defaults from our first and second fully connected layers. Then we make our environment lunar lander v2, and we instantiate an empty score history. This is how we will keep track of our scores. We will let this play 2,000 games. I've already finished running one with 2,000 games. I've got another one going for 3,000 right now. I'll show you the outputs of both when we get to the terminal. I'm not going to wait for it to finish another 2,000 games. It takes a little bit of time, and there's significant run-to-run variation anyway, so you're not going to reproduce my results exactly. Unless we use the same random seeds, which we could do, but are not for this particular tutorial. So we're going to play our episodes by resetting our terminal flag, score, and environment at the top of each episode. Then for each step of the episode, we want to choose an action based on the observation. We want to get the new state, reward, terminal flag, and debug information from the environment. We're going to store the transition in memory. It's observation, action, and reward. And then, very important, you want to set the current state to the new state after you've taken your action. Increment your score, and at the end of every episode, append that score to the agent's score history. And we want to learn. Now, one important distinction here is that this is what is called a Monte Carlo method. So if you're not familiar with Monte Carlo methods, the basic idea is that we have to learn how to play the game by playing the game. The agent starts out not knowing anything about how the environment works and then discovers the rules just by interacting with it. And the learning is conducted at the end of every episode, right? You saw the calculation and learn function iterates over the whole state memory. And so the learning takes place once at the end of every episode. This is in contrast to temporal difference learning methods that also learn by interacting with the environment. It's also model free, but it learns at every single time step, or n time steps in the case of n step temporal difference learning, but in general every time step. That would include algorithms like Q-learning. Actor Critic is also a Monte Carlo method, but it is temporal difference based, so it's learning every single time step. So then we calculate our average score, and I might have misspoken there. I don't think Actor Critic is generally considered a Monte Carlo method. I'm being a little bit loose with my terminology. Specifically, it is a temporal difference learning method. I mean, it's Monte Carlo in the sense that we're just learning from the environment by interacting with it. More precisely, it is model free. So we take the average score of the previous 100 games, and then we want to print some debug information to our terminal. That is the episode number, the score for the prior episode, and the average score. And then at the end of all of the episodes, we'll declare a file name, lunarlander.png, plot learning, call our pass in the score history, the window of 100 games. Again, this is just a simple plot function with some axes labeled. You don't need to do it. You don't really need it. You can just call matplotlib.pyplot here. All right, let's go ahead and run this and see if I made any typos. I do not have the plot learning function. Allow me to import that. So I will say copy. This is on my local machine, so this doesn't apply to you guys. YouTube, reinforcement learning, policy gradient, reinforce, TensorFlow 2, utils.py, copy it here, and then try it. Oh, I also said I would do pip install. I think this is a separate module. I could be wrong. No, it is within the main TensorFlow library. Okay, that's good. So let's try it again. policy gradient network is not defined. That is because I misspelled it. That is in line 16. Policy gradient network has no attribute and actions. I must have forgotten to save it. No, it must be a typo then. Policy gradient object has no attribute. Oh, of course. I see. There is no and actions. That is the downside of talking and typing at the same time. Name action is not defined. That is because it is actions. Okay. So that is here. Okay, so now we are running, and I'm not going to let this finish. I'm going to go ahead and switch over to a separate terminal where I have more than one game going. Sorry, more than one set of episodes going. 1 second. As I was editing this, it finished its run, and I saw that it didn't actually learn. And so I know what went wrong. It is a very simple mistake. So let's take a look at reinforce TF2, and you can see right here I've appended observation everywhere. So that should obviously be action and reward. Otherwise, it does not work. So now that is fixed, and this will of course be correct on my GitHub. Sometimes when I'm recording the YouTube video, I make mistakes. I always fix it before uploading to YouTube, and I'll go ahead and notate this in the video in post-production. But other than that, it's fully functional. The version that's uploaded to GitHub is what I use to produce the high scores of 200 and something odd for the agent. So just a really quick correction here in the interest of being completely transparent. All right, so here is one such session where I ran it for 2,000 games, and you can see in this case it does manage to beat the environment handily, and I will show you the plot from that as well. It has a really sharp increase there at the end with an otherwise linear increase over the vast majority of the games. And this other window is the 3,000 games I'm running, and you see it is achieving a decent score, but it's kind of oscillating around with a general overall upward trend. If you scroll down to 2,000 games, you see it only has a score of around 100, but it's kind of oscillating around a set point of around 130 or so points. So this may very well go ahead and break out and achieve a high score of 200, or it may not. So it's obviously very sensitive to initial conditions. As is pretty much all of these algorithms. When you read the literature, they'll typically average over 5 games and give you the mean, or excuse me, the median plus standard deviation type range. And they will also, if they're really interested in reproducibility, supply a series of random seeds that they used for the generation of those episodes. And you can see here it's kind of hitting 200, 177, so it's getting close to beating the environment here. So it'll probably trend up in the last several hundred games. So I hope that has been helpful. Just to recap, policy gradient methods are a model-free Monte Carlo method that seeks to approximate the agent's policy by interacting with the environment. Again, the policy is a probability distribution that tells you the probability of selecting each of your actions given some state of the environment. It's relatively straightforward, doesn't take much more than 100 lines of code to implement. It's all going to be on my GitHub, link in the description. Also, if you want to learn the how and the why behind all of this, where I go through the papers on DDPG, twin delayed deep deterministic policy gradient, solved actor critic, I cover that on my actor critic course, as well as a deep Q learning course where I cover 3 papers in there as well. Those are linked in the description, and they're on sale right now on Udemy. If you've made it this far, please consider subscribing, hit the like, leave a comment down below, and I'll see you in the next video.